All right, some more examples on multiplication rule and all that good stuff. In baseball, a perfect game is when a pitcher doesn't allow any hitters to reach base in all 9 innings. Historically, pitchers throw a perfect inning, an inning where no hitters reach base, about 40% of the time. So 40% of the time, they get a perfect inning. So to throw a perfect game, a pitcher needs to have 9 perfect innings in a row. So what is the probability that a pitcher throws 9 perfect innings in a row, assuming the pitcher's performance in an inning is independent of his performance in other innings? So we want the probability that he gets at least, probability he gets a perfect inning and another perfect inning and another perfect inning, and he's got to get 9 of those in a row. So the probability he pitches the first inning perfect is 0.4 times. Now, if we assume independence, then the probability he pitches the second one perfect is 0.4. You got 9 of those. So that is 0.4 to the 9th power. So on our calculator, 0.4 to the 9th power. 0.00262. This is 0.000262. I think, is it 3 zeros? 30262. So very rare. However, they play a lot of games, a lot of teams. So they got 30 teams, each playing 162 games. How many perfect games would you expect to see per season? So if there's 30 teams and they play 162 games, that's 4,860 games. Now, however, whenever a game is between 2 teams at the same time, so actually I believe the number of games would be half of this. However, in each of those games they have 2 pitchers, so each team has got a pitcher. So I think we should just use that number. So if we wanted to figure out how many you would expect if we play this many games, and that's the probability, if we just take 0.000262 of 4860, that'll give us our expected number of perfect games you'd see per year. So let's take that times that. 1.27. So you'd expect to see 1.27 perfect games per year in baseball. Historically, though, you only see a perfect game about once every 1 to 5 seasons. So that's like you only see like 0.25 games per year. So the number of games we actually observe is less than what this model would predict. What do you think is the cause of the difference between what's expected and what happens in reality? Well, could be a lot of things. It could be this lack of independence. As the pitchers get into like 6th, 7th, and 8th innings and they have a perfect game going, they might get nervous. The other team might want to avoid giving a pitcher a perfect game. Another reason is the pitchers, usually they don't pitch all 9 innings. So if they get tired, if they get fatigued, as the batters see them more often in a game, they might have a better chance of hitting. Something's wrong with our theoretical model because it doesn't match what happens in reality. So anything like that. At least one. So at least one, anytime you see that in a problem, there's a good chance that we can use the rule of complements to answer a probability statement like this. The idea here is that it's easier to find the complement of an event than the actual event itself. If that ever happens, then find the complement and then subtract it from 1. Challenger shuttle disaster. I don't know if you guys have ever heard of this, but in 1986, the Space Shuttle Challenger exploded at takeoff. All 7 crew members died. One of the crew members was actually a teacher. So whenever I was in school, they put us in the auditorium to watch the teacher get launched up into space. And then all the kids would cry because it blew up. It was it was not a good situation. Anyway, following the disaster, scientists tried to analyze what went wrong. They determined that the failure of these O-rings was the cause. The probability that an O-ring fails is so the probability that a O-ring fails is 0.023. The shuttle had 6 O-rings and all needed to work in order to have the successful launch. So if an O-ring joint succeeds or fails independently, find the probability that at least one of the O-rings fails. So what's the probability that at least 1 in 9 fail? So the reason this is a hard probability to calculate is this is the probability that 1 fails, or 2 fails, or 3 fails, or 4, or 5, or 6 fails. And if you just look at one of these options, 3 fail. That means you could get a fail, 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 and then a success, success, success. Or you could get a fail, success, fail, success, fail, success. Or a fail, fail, success, success, fail, success. You know, each of these outcomes happens many different ways. There's a bunch of different combinations. And we'd have to multiply all these, add them all up, and then do it 2, 3, 1. My point is, this is a really complex, a really long probability to calculate because there's so many different ways that you can get at least one failure. However, if you take the complement of this event, the complement of getting 1, 2, 3, 4, 5, or 6 failures is getting no fails. And the nice thing about this is there's only one way to get 0 fails. You have to have a success and a success and a success 6 times in a row. So 1 minus the probability of a failure is this. The probability of a success is 1 minus that, which is, what is that, 0.977? So this is 0.977 times 0.977 times 0.977, 6 times. So 1 minus 0.977 to the 6th power is 13%. So there's a 13% chance that the launch is going to fail. So obviously, I would hope that nobody would launch a shuttle if there was a 13% chance that it would fail. By the way, the real reason the shuttle actually exploded was because of the failures of these O-rings, but the reason that they failed was because it was cold, like it was 35 degrees or something. They'd never launched these shuttles in this cold of weather. And some people say that they weren't sure how the O-rings performance would be at these cold temperatures, but other stories say that there were scientists, there was like one guy or something that knew that those O-rings were going to fail at this cold weather and recommended that the launch be canceled. And apparently he was overridden by somebody that was higher up or something. I don't know. It was a disaster to be sure, but something that could have been avoided if engineers would have done a better job doing their job. I think this is the last one. Last one, more batteries. We looked at this before, I think. We have a bag with 6 good batteries and 4 bad batteries. So that's a total of 10 total batteries. Suppose we select batteries from the bag without replacement. Find the probability we get 5 good batteries in a row. So that's the probability we get a good and a good and a good. So the first one is good. Well, 6 out of 10 are good. Times, but we're not putting them back. So once I take a good one out, I now only have 5 good ones left and a total of 9 left over. Times 4 out of 8, times 3 out of 7. And when you select that last battery, there's 6 in the drawer and only 2 of them are good. All right, I paused it so I could put in my calculator. 65432, 109876. Control Enter. 2.02. I'm going to go 0238. 0238. So there's about a 2% chance, a little more than a 2% chance that you're going to get all 5 good batteries. Find the probability we select exactly 2 good batteries when we pick 3. So that's a probability that we get 2 and 3. So that means I could get a good, good, bad, or a good, bad, good, or a bad, good, good. So we have to calculate all the different ways that we can get 2 batteries in 3 that are good. And thankfully, unlike this example up here where there was so many, this can only happen 3 ways, so it's kind of manageable. All right, so good, good, bad. So I got to get a good, and then another good, and then a bad. So if I, 4 bad. So 4 out of 8. Plus, or is plus. Now I got to get a good first, so that's 6 out of 10. A bad second, so there's 4 bad and 9 left over. And then the last one's got to be good. So that's 5 good ones left over in 8. And lastly, we got to get a bad, so that's 4 out of 10. And then a good, 6 out of 9. And then another good, 5 out of 8. And if you notice, these 3 things are all actually the exact same expression, just with different orders. So that makes it a little bit easier to calculate. I'm going to pause it while I put it in my calculator. 654, 1098, 654, 1098. And then what I'm going to do is actually multiply this entire thing by 3, because there's 3 of them. Oh my gosh, how'd that work for 50%? Very good. Okay, find the probability that we get at least 1 bad battery when picking 4. So this is the probability we get at least 1 bad in 4. So I could calculate the probability that we get 1 bad, or 2 bad, or 3 bad, or 4 bad. And then for each one of those, I'd have to find all the combinations of getting, for example, 2 bad. This is going to get a little bit overwhelming. So, and you should recognize the at least 1. So let's use the rule of complements. This is 1 minus the probability of, what's the complement of getting at least 1 bad? At least 1 bad is 1 bad, 2 bad, 3 bad, or 4 bad. So the opposite of that, or the complement of that, is getting no bad in 4. And the nice thing about this is this only happens one way. The first one's got to be not bad, so good. So 6 out of 10, 5 out of 9, 4 out of 8, 3 out of 7. So if I type that in my calculator, 1 minus 6543, I think that's right, hopefully, 929, 0.929. So the probability to get at least 1 battery when you're picking 3 is actually pretty high. And it is the complement of getting all good batteries in 4, right? All right, that's kind of it for this section. I think there's one more video that'll go through these last few examples. Thank you.